everyone to the second part of episode 2 of this RDC webinar. I am assuming that here at the beginning that you attended mine, or at least you watch it over the internet and the link that is available. So I'm going to start today, and I'm going to do some data analysis and applications. So the first part is going to be how the data is analyzed and fit to the structures. Then I want to give a live example on how to use the fitting software. And at the end, I will show some applications. So if we go back, we've already seen this slide. So the dipolar coupling, as it is normally in solid state for a static molecule, we already seen the dipolar coupling depends on this constant kappa. The constant depends also on the distance. The constant depends on the product of the gyromagnetic ratio. So here it is very important, because if you want to collect RDCs of proton-proton, that would be the highest value. If you want to collect RDCs for proton-carbon, then carbon is 1/4, and then if you want to collect for carbon-carbon, it's even smaller. So also this ratio determines the size of the value of the dipolar coupling. On the other side, we already said that depends on the cosine square of theta, when theta is the angle of the internuclear vector. This internuclear vector can be a couple of magnetically active spins, and they can be bonded or non-bonded. And then what I showed you last time, and I have also to make a correction here, because in my slide, in my first presentation, it said that this one was 46.6 kilohertz for a CH bond parallel to the magnetic field, but it's negative 46.6 because the K for, or kappa for the CH bond is minus 90. So my apologies for this mistake, but now it's corrected here. So let's move forward, and then let's analyze the values of the dipolar coupling, in respect to the angle. So for example, so if the maximum value for cosine square of theta is 1, for when the angle theta is 0 or pi. So that means when it is parallel to the magnetic field. So cosine square is 1, so then the D maximum is 2/3 of K over the distance of the internuclear vector. So if we analyze the value for the minimum value, so the minimum value will be when cosine square is 0, but it will be 0 if the angle is pi over 2, 90 degrees, or 3 pi over 2, that is 270 degrees. So if it is 0 here, then the dipolar coupling is minus 1/3 kappa over the distance. So then you can see now that this value is half of the value. So when the internuclear vector is perpendicular to the magnetic field, is half of the value of when it is parallel, and it changed the sign. So keep in mind this 2/3 of K over R to the third power, and the minus 1/3, because we will come back and I will show you something very interesting. In this representation, now you can see, and then you can represent, and this is the two lobules of the negative values of for a CH, for example. So this is Dij maximum, and then here, as I told you, is minus Dij over 2. So you should expect that the size of the dipolar coupling will be half. Of course, in this case, in solid state, but when we have the alignment tensor can have different values that are not just like this. And the other example is that when the angle of the internuclear vector is 54.7, okay, then when it is and then it is in the intersection of the positive and the negative lobule, the dipolar coupling, so cosine square of 54.7 is 1/3. So 1/3 minus 1/3 is 0. And then this is when it vanishes, and this is what we know as the magic angle. We already discussed in the last webinar that for an isotropic solution, the dipolar coupling average by isotropic tumbling, and then also in solution or when the molecules are in motion, this cosine square is not longer an angle. You know, it's time average, so it's time dependent. And then also we discussed in the last webinar that this cosine square of theta can be expressed in terms of a probability, that is the probability tensor. Also, what we arrived last in the last webinar, so we said that based on, I strongly recommend to read this article by Kramer and et al. In Concept in Magnetic Resonance. So this cosine square, you know, is the time average of cosine square of theta can be represented in a tensorial form in this way. So here is an expansion. So where these are the coordinates, these are the coordinates of the internuclear vector. This is the coordinates, the R transpose, and here are the coordinates with R. And then this is how you can calculate. If you know the probability tensor and the coordinate, you can calculate this value. Also, we said that when you will see in the literature, you will see the alignment tensor, that is the probability tensor minus 1/3 of the unitary tensor. And then you can, we arrive also to the conclusion that this cosine square, the average in term, minus 1/3 is equal to this in tensorial form. And so here is what I would call the generalized equation for the dipolar coupling, because if you use the tensorial form, you know, it doesn't matter if it is in solid state, in isotropic solution, or in any anisotropic conditions. And here is an expansion of this equation. So for fun, I decided to do this so you can understand better how RDCs are calculated here. But in solid state, the magnetic field B0 has a probability of 1 along the z-axis. So the probability tensor for a molecule in a static condition is this, is 0, 0, 1. So if you subtract, you know, minus 1/3 in order to calculate the alignment tensor, so then if we calculate this, so this should be the alignment tensor in solid state. Well, it is not an alignment tensor, it's just a tensor that represents full alignment, 100% of alignment. So here is how the equation to calculate, so we can calculate a DIG value, you know, using this alignment tensor, you know, in solid state in the tensorial form, and I will show you a couple of examples. So for example, so we have three different situations. When the internuclear vector is parallel to the magnetic field, and we already said that Dij is 2/3 K over, you know, the R to the third power. So if it is perpendicular, if it is in X or if it is in Y, you know, we already said that Dij is minus 1/3 with this constant, and of course this is not the constant, this is the distance. And if it is in magic angle, and so the projection will be the third. So this will be the dipolar coupling will be 0, and this will be the angle 54.7 that we said is the magic angle. So for the internuclear vector Ij along Z, okay, we can replace here. So if it is along Z, the vector that represent that the R that represent that orientation is 0, 0, 1, and then times this. So 1, when you multiply, it will read this value, and 0 read this one, 0 read this one, so it's 0, and then the product is just 2/3. So we get exactly the same result if we use the cosine square or if we use the tensorial form. This is beautiful. If we do this for the internuclear vector along X or Y, let's say X, so this will be 1, 0, 0, and then 1, 0, 0, and then 0, 0 will read these two values 0, but this one will be 1 times minus 1/3 times 1. So then we ended up that the dipolar coupling value for a vector that is perpendicular to the magnetic field is minus 1/3. It's exactly the same result. And if we do the same calculation for an internuclear vector that is in magic angle, and then we replace here the values, and then we do all this math. Okay, I'm not gonna read this, but then if you follow all this calculation, then the dipolar coupling vanish. So said that, I would like to switch gears here to a topic because there were two papers that created excitement in the NMR community. One was published in 2007, and the other was published in 2011. And one was claiming that it is possible to assign absolute configuration by RDCs. And the other article also did the same. And in 2011, these articles were cited several times, at least 20 citations, and this is wrong. And why this is wrong? Because if we use just the equation of RDCs, for example, when we use just this one in solid state, you can see, because this is a cosine square, and then I just draw this example for this compound. So the equation of dipolar coupling is insensitive to inversion and reflection. That is why it's another NMR parameter that you cannot determine absolute configuration. So you can only determine relative configuration. And here what I did is I did the mirror image, the inversions, and then I calculated for different angles for this method group. And then you can see that regardless of the angle, and when we do the reflection, then the cosine square of 29, of 151, 209, or 331 degree is 0.76. It's the same. So all these different orientation will give you exactly the same dipolar coupling. So as I said, dipolar coupling is insensitive to inversion or plane reflection symmetry operations. Well, let's look at the same example, but let's look at the same example with the equation in tensorial form. So if we look at the equation in tensorial form, so if you have your coordinates x, y, z of the molecule, then R is the enantiomorphous configuration of minus R. So it is not, I would say, it is really easy when you want to create the enantiomer coordinates, you just multiply by -1. So in this equation, if you do this with one enantiomer that is R, so this will give you the same value if you use -R, because minus is positive. So again, here it is pretty obvious that that you will obtain the same set of RDCs for both enantiomers. So it is not possible. So they equally fit, enantiomers equally fit to the equation. And because of this, a group of scientists that is most of the leaders in the field here, so we decided to write a critique that was published in 2012, and then you can see the title that it is enantiomer assignment possible by NMR spectroscopy using residual dipolar coupling from chiral non-racemic alignment media. And then it's a critical segment, so I recommend you to read this article. If you don't have access, just drop me an email and I will send you the PDF. And now let's go to see some properties of the alignment tensor. So in order to understand how to analyze the data. Well, the alignment tensor is symmetrical. So that means that this half is mirror images is the same of this half. So as it is said here, so AYX is equal to AXY and so on. And then it's traceless. Traceless means that the sum is equal to 0. So AXX plus AYY, sorry, is equal to minus AZC. So if you know two values, you can know the other one. So in fact, the alignment tensor has 5 independent values. When we collect RDCs, and now we're not going to talk about the alignment media, so let's say that you were able to, using any alignment media, any alignment medium, sorry, you collected a set of RDCs, and now what you want to do is you want to solve your structure. So the alignment tensor is not known. You don't know. There's no way to know the alignment tensor unless you do molecular dynamics, and even today it is very difficult, especially for small molecules, or almost impossible to simulate and calculate the alignment tensor. So we need to determine the alignment tensor experimentally. So in order to determine the alignment tensor experimentally, we need to know at least 5 RDCs. So if you know 5 RDCs, what you have is you have to solve this equation of 5 unknowns, and then you need 5 independent values. Then what you do is you fit this data, and then you solve this equation by fitting this data using singular value decomposition in the program MSpin. And then the quality of the fit is a Q factor, and then we will see that in the next slide. But before going to that slide, I want to show you this. So I said that we need 5 independent values. So normally 5 independent values is 5 non-parallel internuclear vectors, and at least 2 have to be out of the plane. And this is the example of menthol. And then in menthol, you can see that, for example, you have a lot of parallels. So all the green ones are parallel, all the red ones are parallel, and the pink are parallel, and the yellow. So here, in fact, you cannot use all of these because are dependent. So for menthol, you have only 4 independent values. So you cannot solve the structure of menthol because you need other RDC, let's say proton, or proton, carbon, if you want to solve this structure. So what do? So now, when you want to determine relative configuration, you need to know all your options. So suppose that you have a molecule that is that has n chiral carbons, so you have 2 to the n minus 1 possible diastereomers. So you have to generate all your possible structures, and then you have to measure more than 5 RDCs, and then what you do is the software, by singular value decomposition, it will fit your set of RDC to each structure in your set. But you have to make sure that you have all of the structures in your set. So you have to make sure that all your configurational space is complete. Once you do that, then the software will calculate an alignment tensor. It doesn't matter. It will get the best alignment tensor, and then it will back calculate the RDCs. So the calculated RDCs will be compared with the experimental, and this comparison is done by this Q factor. If the calculated RDCs are identical to the experimental values, so Q is 0, but it's never 0. The reason why it is never 0 is because you have errors when you measure your RDCs, and also you have structural noise. And I would say that if you get a Q factor between 0 and 0.5, it's an excellent Q factor. If you get less than 0.1, it's good Q factor. And then if you get above 1.1, well, it's not that good. But here is an example in which the lowest Q factor will give you the comparison, and here is a Q factor of 0.045 for this structure. I will apologize because I don't want to offend your intelligence, but I found this a very nice example because probably when we were, I don't know, many of you, when you were kids, so I don't know, I used to play this game that was, it was in these magazines, and it was the game of the silhouettes. And what you do? So what you do is, if you have here objects, and then you have their silhouette, so you have to choose, which one is the silhouette that match the object. So let's say that these different type of object will be the molecular constitution, but if I have the same type of molecule and I have a different configuration, I will say that I have different fishes. So here, so if I fit my RDC data, then I will find this fit to all these structures, and this will be the best fit. And then in this case, so this will be the best fit for this fish. So what I'm coming here is that RDCs are to the molecules as the silhouettes are to the objects. So this is an you know in layman language. So how do you explain the fitting? So what you do is you have always a set of RDCs that will fit to the structure, but there will be one set of RDC that will fit in the same way that the silhouette fits to the object. There is a nice article that was published in 2012, written by my colleague Armando Navarro-Vazquez, who wrote the program MSpin, and so you can go and read these articles and learn more about MSpin. But I'm expecting that my colleague Armando will also give webinars, especially on MSpin. And here is, I will show you, for example, something that is really nice. What we did here is we use the Bruker CMC-SE software, and we perform this analysis manually now, and then what we did is we fed the software with a set. You can use any structural elucidation software, because any case-based software nowadays we give you your 2D structure. So it's been the constitution. So we fed with this data. Then we generated 146 possible compounds, and using carbon chemical shift, predicted versus calculated, that was the constitution that have rank number 1. So what we did is we generated by DFT all the possible configurations, and then we got the configuration. We ran the RDCs, and we got this quality factor for this configuration, and this was the correct structure. So this was in one shot. But look, did I use NOE? No. Did I use J-coupling? No. Did I use chemical shift? No. I just used RDCs, and then I just went from here to here and from here to here in one shot. Here is really the power of RDCs. Now stop here just for a second, and then I'm going to show you how to fit data in the software MSpin. Well, so the input table for MSpin is very easy. It's very simple, very straightforward. So what you have to do is you have to give the number of the carbon in the structure. The proton and the RDC is just an ASCII table. So you create this ASCII table. This is in the paper written by Armando, and then you have to generate all the possible structures. So what I'm going to do here is another thing that is very nice of this software is that here I have all the I have 8 configuration. Some of them are almost impossible to produce. That's why there are 8 and not more. But then you can do drag and drop here. So here we have all the possible structures, and here I have the window of all the possible structures. So you can see all of them here in the program. And what I'm going to do for visualize better, I'm going to change the view to the background color. I prefer to use it white here. And then I'm going to change to sticks. So this is nice. Okay? And here you can see all the possible structures of stringing. Now I will go to the calculation module. And let's This is not. So I need to get the RDCs, analysis, RDCs, RDCs window. Here I have the RDCs window. So now what I have to do, I have to load the input table. So I'm going to load the input table from here. And now the data here. So if I click here, I will see the data next to each pair of internuclear vectors. Then most of them are CH. And then what I'm using here is I'm using the sum over 2 of the in the methyl group on the methylene, sorry. So I don't need to do the diastereotopic assignment, but I have to tell the software that I am averaging methylenes. And if I have methyl group, I have to tell the software that I average methyl group. And now, just what I do is go back to calculate, say calculate is done. The SVD is done for all the structure. Show results. And here I have the experimental versus calculated, and I have all the conformation and the Q factor. And structure number 6, that one is the one that gave a Q factor of 0.048, is the correct structure. The program also gives you the alignment tensor here. Something very important is that if you have too many parallel vectors, you will get the condition number of the SVD that is bad, so you should get less than 10. And something that also the program gives you is the GDO, global degree of order. So this set of RDC is telling me that strychnine in this compressed gel has a degree of order of 7.44 10 to the negative 4. So this is the degree of alignment that we talk, that needs to be in the order of 0.1 or 0.1%. And then another feature that I really like of this software is that if we remove now the RDCs from the structure, we can visualize the alignment tensor in display. And here we show the alignment tensor. There. And then what is this information telling me? See, there, the alignment tensor. The alignment tensor is not like in solid state, because since it is a probability, so it is telling me the negative lobule, I will make it bigger. So the negative lobule, see, this is telling me that this molecule, see, the plane of the molecule should be, it has a preference to be oriented perpendicular to the magnetic field, because this molecule was aligned in a compressed gel. Imagine that the cavities are flat here and flat here, so this is the preference. So it's telling you that this is the preferred alignment. See the probabilities, these are negative RDCs, these are positive RDCs, and here the lobule is bigger. And if this molecule were aligned, if this molecule were aligned, I don't have a mouse with a wheel, in a stretch gel, it will be aligned like this. And then this lobule will be rotated and will be parallel to the plane. So also this is very nice also to give you the way the molecule is aligned in your alignment medium. Well, I hope you like this. Let me now go back to my presentation. I will close this and come back to my presentation here and continue. Well, it took me 30 seconds. So let's say this was working very well for rigid structures, but in conventional NMR, if we want to do a conformational analysis, well, normally what we do is the average chemical shift of the average J is the populated average, and then you use you have, for example, a two-side fast change conformation system. Then it's the population of A times the chemical shift of A plus the population of B times the chemical shift of B. The same with J. But when it comes to RDCs, if the different conformations have different shapes, they will align differently, so they have to be defined by two different tensors. But if the conformations are similar in shape, you can assume that the tensor of the alignment is the same for both conformation, and then you can do what we call the single tensor approximation, in which the tensor for conformer A is equal to the tensor for conformer B. Then we just remove A outside, and then you ended up in a situation like this. And then you have to align the molecules. So probably Armando will tell you this more in detail when he teaches his webinar. So I decided to classify now the use of RDCs in 3 different scenarios. So scenario number 1 is rigid molecules, 1 conformation per configuration, or a flexible molecule with a single dominant conformation. This is easy. This is exactly what we did for string 9. Then we have a scenario number 2 in which you have moderate flexibility, few conformations, not significant difference in overall shape between the conformers. The single tensor approximation can be used. For example, this is the case. So this conformation is between these 2 species, and then so this one is the dominant of the alignment. You overlap, and then you fit to the overlap structure, and then you average these 2 based on population. And that is there are many cases like that, and then you have to analyze case by case. But then when you have high flexibility, several conformations, significant difference in shape between conformers, the single tensor approximation doesn't work. Poor fitting is observed. Possible solution to this problem now, I know that Armando, Burkhard-Louis, and Ulrich Stemmer are working on these molecular dynamics with orientational constraint. And other options are, I think that Armando is working in some project. I think that he's going to present at the ENC a work on using maximum entropy and multi-tensor fitting. And then let's go to see some examples. So I isolated this compound during my graduate studies, and I had to do semi-synthesis because the difference between the alpha and the beta is almost like in a double bond. So the use of conventional NMR didn't work. So we used the traditional method, the method that originally Burkhard-Louis proposed. So with the PMMA, we collected 10 RDCs, and then we just generated the structures, and then we feed the RDCs, and in one shot we determined that it was the alpha, the Q factor was 0.048 and the Q factor 0.22. So imagine 10 years ago, or when I did my PhD, that was science fiction. So now, in one shot we can do configuration of problematic structures. Another example here in natural product is that this structure is a natural product isolated from a plant called Javorosa, and then here we have 4 chiral carbons, and then we have I think this is kind of a scenario number 2. So we collected 4 RDCs, but by NOE and J coupling, when we try to solve this, we got 3 possible structures. So 3 possible configurations. So we got limitations using NOE and J coupling. So we collected the RDCs, we fit to 24 conformation configuration combination, and the best fit was done by 23x, 24x. In fact, it was SSSS, and this was published here. This is eburnammonine. It's an alkaloid from my colleague Elena Maruenda from Peru. So she isolated a compound in which the ethyl group was oxidized, and then there is an OH group here. There was a quaternary carbon here, so we couldn't get J's, and then this was rotating. So we did the same. We collected RDCs, and then we got the SRS configuration in one shot. And also we did absolute configuration by comparing the calculated ECD with the experimental ECD. This is really a beautiful example. A colleague of mine came to a conference that I gave about RDCs, and then she isolated these limonoids derivatives. So in this case, this structure was solved by X-rays. But then she isolated this compound that then she acetylated in the mixture and obtained the 2 acetylated isomers that can be, one can be R and the other can be S, and the difference in the NMR was this the signal of this chemical shift, the chemical shift of proton 23. That is this one. And so look, this center is far, so you cannot use NOE. So what we did is we generated the structure. We were very lucky because we got only one rotamer per structure. We collected RDCs, and here, this example we had to use a quadruple recoupling of 17 Hz because this molecule was aligning strongly, and it was able, using the compression device, because we relaxed the gel, and then we started to see the signals, and we measured RDCs for carbon 2, 3, 5, 15, 22, 23, 29, and 30. And then look, the fitting of the data to the structure for compound 6, we got this nice fitting for the R isomer at 23, and for compound 7, we got this fitting for the for 23S. So in one shot, we measure both structures, and we determine the the relative configuration of this CH respect to the skeleton. But since we know the absolute of the skeleton, we got the absolute configuration. So this is these are no published results, and then right now we are going to submit the paper. And then I want to just switch and take just a few more minutes to synthetic compounds. So let me tell you, I think that the RDCs will benefit a lot to organic chemists in the lab. So if this technology is now easy to use, and then the organic chemists, they have more compounds than the natural product chemists. Natural product chemists normally have 1 milligram. We did that, the other study, we did it with only, I think that less than 2 milligrams. So my colleague from Rosario, Argentina, Mirta Michne, she wanted to make this compound, and then the reaction went over to these compounds. So, and then again, we use RDCs, and we determine the configuration. And here is a case of single tensor in which we just fit to a single tensor, and this paper was published in OBC. So I encourage you to read more. I just want to show you examples. This is another case in which my colleague wanted to obtain this product, but then the reaction went over, and then obtained this compound 4. So the possible structures were, we were thinking about this structure, and then when we ran the adequate, we realized that this carbon was coupled to one of the carbonyls, so we arranged the structure to something like this. But then when we ran the structure elucidator from ACD lab, it told us, oh, you have another possible structure. So we ended up with 2 possible constitutions. But then we did RDCs, and then quickly we removed the constitution with very high Q factor for the oxetane, and then we solved the structure of the oxygen. In this case, this molecule is so small that we had to align this in PELG. It's the only time that I use a liquid crystal. And recently, a colleague here in the chemistry department, Professor Noonan, studied this reaction, this Diels-Alder, and then he wanted to know the configuration of his molecules. And so in this case, the reaction could give the regio isomers, and in this case, the endo or the exo. So we did the same. We collected RDCs, and in this case was a mixture. See, here you can see the mixture, 75-25. And then we collected RDCs to the mixtures. And the nice story is that I asked my colleague, how much sample do you have? And he said, I don't know, I have 100 milligrams. Is that okay with you? Of course, I'm rich here. So we just put probably a couple of milligrams in the gel. We collected the RDCs, and then we generated all the possible models. That was the cis with the methyl group in 9, trans here in 712 with the methyl group in 10, and then we generated all the possible configuration. It was the regio isomer and the cis and trans, and then we fit. So the major compound was the cis C9, and that is this one, and the minor compound was cis in C10. So in one shot, we got the residual isomers, and also we got the configuration here in the fusion of the ring that is very, very difficult to get by conventional NMR. In the case of the exo and the endo, also we analyzed the mixture. By integral, the mixture was 7822. So we collected RDCs. We generated the cis endo, the trans endo, the cis exo, the trans exo, and then so we quickly determined that the best Q factor for the major compound was the cis endo, and for the minor compound was the cis exo. And well, and that's it. So thank you for attending. So I will check if there are some questions. So this is the end of my talk. It was around 40 minutes. Let me see if there are questions. I will be happy to answer. Oh, yeah, there are questions here.